Now we find ourselves here at the last subtopic of Chapter 5, so we've learned a lot about compounds and their bonds, and hopefully you've gotten the hang of all these different, sometimes tricky concepts. So again, hopefully you've spent the time and worked the problems to get yourself familiar with these ideas, and you're ready to think about this last section here where we'll talk about attractive forces. As we consider those attractive forces in compounds, again, we're going to have to go back to our basics and understand that things are different when we're talking about ionic compounds versus covalent compounds. The metals themselves, which are roughly 3/4 of the elements, if we're talking about just their elemental state, their bonding is its own unique thing, and certainly an interesting topic that we really don't address much in this course. We just called it a sort of a sea of electrons. That's what allows metals to conduct electricity and heat very well. So we're mainly focused on ionic and covalent compounds and the attractive forces that they experience. Okay, so the ionic compounds were the first we discussed here in Chapter 5, so let's review those. Ionic bonds are very strong, therefore they require large amounts of energy to break. It's the full positive and negative ions charges that is holding that lattice together, and that explains the high melting points we experience. In order to actually melt an ionic solid like sodium chloride, you have to put a lot of heat energy in because you actually have to break the positive-negative ion attraction. That electrostatic charge attraction for them has to be overcome to allow them to be mobile enough to mix around in a liquid form. If we think now about covalent compounds, which are very discrete, right? They tend to be nice and small, at least the examples we've looked at. So those attractive forces tend to be weaker than ionic bonds, right? And therefore they require far less energy to break. We're not actually breaking the covalent bonds themselves within the molecule. We're breaking the interactions that the molecules are experiencing with each other. And that's why we tend to see much lower melting points for covalent compounds than for ionic compounds. So the intermolecular forces, as we call them, the things that are keeping the molecules together in the lattice of, say, an ice crystal for molecular water, or HCl molecules. If we're thinking about those sorts of attractive forces between molecules, we have either dipole-dipole attractions, which require us to have a dipole, a polar molecule. We have dispersion forces, which doesn't require anything special. Actually, all molecules experience this, where it's just a temporary shift in the electron density. And then finally, there's hydrogen bonding, which is not a true chemical bond, but when you have hydrogen bound to OF or N, you can get a very strong sort of interaction that we'll talk about in a few moments. Alright, so if we consider those dipole-dipole attractions, right, if you have polar molecules, they're going to have attractive forces between molecules in a sample, and we call those dipole-dipole attractions. So if we think about HCl, which is a great example of a polar molecule, partial positive hydrogen, partial negative chlorine end, it's pretty substantial, the electronegativity difference, so we see a pretty strong polarity to that HCl molecule. But when we're dealing with samples in the lab, we're dealing with many, many molecules of HCl. So we have to consider the fact that those molecules will line up with each other so that their dipoles complement. So the partial negative of the first chlorine in the hydrogen chloride molecule on our left aligns with the partial positive hydrogen end of its neighbor to the right. So this allows for a fairly nice interaction, and it explains why dipoles have generally higher melting points and boiling points than nonpolar substances if all other things are equal. So we said that hydrogen bonds aren't true chemical bonds, but they are very extreme examples of dipole-dipole attractions. So these only tend to happen with small, very electronegative elements like nitrogen, oxygen, and fluorine. If you remember our second period of the periodic table, we said fluorine's the boss when it comes to electronegativity. It's 4.0 is the value given to it. at least the value that we've learned. Oxygen is 3.5, and then nitrogen is 2.0. So as we moved each position to the left, we lost a 0.5 electronegativity unit. So these are small and quite electronegative central atoms, and when they bond with hydrogen, there's such a disparate electronegativity difference that you really start to expose that hydrogen nucleus. The oxygen or fluorine or nitrogen atom is getting the electrons most of the time in that bond, and so the hydrogen's building up a very, very significant partial positive, such that you're exposing that hydrogen nucleus and making it really ripe to engage in a very strong dipole-dipole attraction with the lone pair of the OF or N on the neighbor. So that's what you see here. Water does a great job of this. It's aligning itself such that it can experience 4 hydrogen bonding interactions, and that allows water to be a liquid when most every other small molecule, something with an atomic mass of 18 atomic mass units, right, the oxygen and the 2 hydrogens, it's a very small molecule to be a liquid at room temperature and pressure, and that just underscores how strong those hydrogen bonds are. HF and H3, they can't make as many hydrogen bonds with neighboring molecules, so at room temperature and pressure, those two are both gases, whereas water is a liquid. Hydrogen bonding is very important for biological applications like the double helix, DNA, complementary DNA base pairs engage in hydrogen bonding, and it's strong enough to keep that DNA tightly bound when it's not active, but they're not so strong that you can't break it open and unzip those double helices to make more copies of the DNA. And finally, for the dispersion forces, sometimes called London forces after the scientist London who discovered them, they're very weak as a comparison to the dipole-dipole or the hydrogen bonding. And they're weak because they're just temporary dipoles. As the 2 electron clouds approach each other, just that approach is going to cause partial negative and partial positive to develop, because they'll start to repel, and that'll cause the electron cloud of one molecule to retreat a little bit, and that you'll set up a temporary dipole, just a very weak dipole, not like a polar molecule that has a permanent dipole. So these tend to be the major intermolecular force when we're dealing with nonpolar molecules. And that's one reason that you see in the family 17 or group 7A, the halogens. As you move down, these nonpolar dispersion forces get more significant as you get a bigger electron cloud. So fluorine and chlorine, F2 and Cl2, those are both gases at room temperature and pressure. Br2 is our only nonmetal that's a liquid at room temperature and pressure. Mercury's our other liquid element, but that's a metal. And then finally, iodine is a solid at room temperature and pressure. So you see the strength of the dispersion forces increases as the size of the electron cloud increases, because you've got a bigger cloud to polarize and set up those temporary dipoles. So that's why the greatest interaction results in iodine's case in that family, and the iodine molecules get the temporary dipoles that are so significant that it's a solid at room temperature and pressure, whereas bromine's a liquid and chlorine and fluorine are gases. Okay, so we have table 5.17 here, a comparison of bonding and attractive forces. This is a rule of thumb type table. We do have a case of covalent bonding that's very, very strong, and that's diamond. Diamond is an example of what we call a covalent network solid, where you have carbon-carbon bonds just extending infinitely, and that's a very strong interaction. So don't be misled. We're just doing the generalizations here. In general, the ionic bond tends to be very strong, and we tend to have very high melting points, high boiling points for ionic substances. For covalent substances, we tend to have lower strength bonding interactions, and therefore we tend to be liquids or gases at room temperature and pressure, whereas ionic substances tend to be almost exclusively solids. So if we think about melting points and attractive forces, it would make sense that the stronger the attractive force between ions or molecules, the higher the melting point. So ionic compounds, which have that true chemical bond of electrostatic interaction, positive ions and negative ions attracting each other, therefore they have the highest melting points, because to melt the ionic solids, you've got to allow those positive ions and negative ions to flow around each other. So you have to really break that very stable crystal lattice. And then to make them a gas, you have to separate those ions, which takes even more energy. For covalent molecules, we're not breaking any chemical bonds here. We're just taking the covalent molecules and interrupting the interaction they have with their neighbors. And so because you're not breaking any true chemical bonds, you're just interrupting those intermolecular forces, as we call them, the London or dispersion forces, the dipole-dipole, or the hydrogen bonding, which is not a true chemical bond, but an extreme form of dipole-dipole. That's why we expect lower melting points, because to break those up doesn't require as much energy as to break up the crystal lattice of our typical ionic solid. Okay, so if we're focusing now on the attractive forces between covalent molecules, these will vary depending on which one we're talking about. The stronger the attractive force, the higher the melting point we'd predict. So if you have hydrogen bonds, that's the strongest type of dipole-dipole attraction we can have, and that requires the greatest energy to break. Next would be the dipole-dipole, and then finally the dispersion are the weakest. So you tend to see the lowest melting points when you have just dispersion forces, then intermediate melting points for dipole-dipole, and then finally the highest melting points tend to be for substances that can experience hydrogen bonding. That's a rule of thumb. It also matters on the size of the molecule. So if you think about oils tend to be fatty acids, and they tend to be pretty nonpolar, tend to be mostly dispersion forces, a little bit of dipole at the end, and oil is a liquid at a greater range than water, which can do hydrogen bonding. So if you've got a really big molecule, you've got a lot of dispersion forces that can result in a higher melting point, higher boiling point than a very small molecule like water that has hydrogen bonding possibilities. So it's rules of thumb, again, generalizations. So in general, if you can do the hydrogen bonding, you'll have the highest melting point, followed by the dipole-dipole, followed by the dispersion force. So that's our rule of thumb, and that's what you'll expect to see on the homework sets and the tests. But just realize it does get more complicated because we have to consider the size of the electron cloud, which is directly a result of the number of atoms and the size of the atoms involved in the bonding. So here we are at table 5.18. We have the melting points of selected substances, and we see the ionic examples, magnesium fluoride and sodium chloride. They're very high melting, over 800 for both, over 1200 for the magnesium fluoride. So very strong, stable ionic bonds there. For hydrogen bonding, water, of course, we know the melting point 0 degrees Celsius. Ammonia is a minus 78. So they can both do hydrogen bonding, but because water can engage in 4 hydrogen bonding pairs, it has an even stronger interaction than nitrogen in the ammonia, which again can't engage in so many hydrogen bonding complements. Next, we see the dipole-dipole interactions, and again we see some lower melting points, although HCl and HBr do both melt at lower temperatures. HI melts at a higher temperature than NH3. So just because the NH3 does hydrogen bonding, HI is a very big, the iodine at least, is a very big atom, and therefore you get a significant dipole-dipole attraction and even significant dispersion forces. As we look down, again, bromine has a melting point above that of NH3 and HI, HBr, and HCl for that matter, because it's a big molecule and it has pretty significant dispersion forces that can build up because of that large electron cloud. Notice chlorine and fluorine significantly lower, and methane, again, a very low melting point because it has typically dispersion forces only. So we have that example here from the table, and again, that should make sense that we have the strongest interaction in the ionic bonding examples, followed by the hydrogen bonding examples, and then in general, dipole-dipole and dispersion. Alright, so let's end this subtopic and this whole chapter with a learning check. So your challenge here is to identify the main type of attractive forces for each of the following compounds. Would it be ionic bonds, dipole-dipole interactions, hydrogen bonds, or dispersion forces? Go ahead, pause the video, take your time. It'll take a little while to figure these out. And then once you've done that, start us back up and we'll see how you did. Okay, so hopefully your list looks like mine. This was quite involved because you had to do Lewis structures for the molecular substances. The ionic substance, number 4 there, KCl, that should have jumped out at you as a metal and a nonmetal. The others are just nonmetals bonding with other nonmetals. And so therefore you had to draw the Lewis structures and figure that out after you have the electron dot diagram. Do you have a polar molecule or a nonpolar molecule? If you have a polar molecule, do you have a hydrogen bonded directly to N, O, or F? And therefore you would be able to experience hydrogen bonds. If you have a polar molecule that doesn't satisfy that, then it's dipole-dipole. And if you have a nonpolar molecule, you have just the dispersion forces as the most significant and the main type of attraction. So NCl3, you have that lone pair that allows us to have a net polarity to the molecule because the NCl bond is polar. As we said, if you've got a lone pair on the central atom and you've got polar bonds, in our course you'll end up with a polar molecule. That's what we see again in number 2 with water, but because we have a polar molecule, a dipole, that has H directly connected to O, we have hydrogen bonding possible. Number 3, Br2, it's bromine exactly balanced by the other bromine, and therefore no electronegativity difference, no polar bonds, therefore no chance of being a polar molecule. We're a nonpolar molecule, and therefore dispersion is our number 1 type of interaction. For KCl, we already mentioned that that's a metal and a nonmetal, so we'd expect an ionic bond. And finally, for NH3, we have the same sort of situation. It looks a lot like NCl3, except we have just a single bond to each hydrogen. We don't fill out the lone pairs around hydrogen because it can't have any. And we end up with another case where we have a polar molecule because that lone pair on nitrogen allows for an asymmetry in the bond polarity that doesn't cancel the overall molecule, and therefore having a polar molecule, we have to consider either dipole-dipole or hydrogen bonding. In this case, N directly bonded to H gives us the possibility for hydrogen bonds. So, as I said, Chapter 5 is a really big one for us. It's the most important chapter for going into 142. That's not to discount all the stuff we'll do in Chapters 6, 7, 8, 9, 10, but it's, again, a very significant chapter for us. And if you're struggling with it, don't just give up or throw in the towel on those exam questions. Make sure you do the homework set, do additional practice problems if you need the additional practice, and reach out to me if you still just aren't getting it and you're spinning your wheels and it's not making sense, because it is important and it is something that I'd be happy to help with if you need it. But otherwise, the hope, the dream is that you're doing super, things are going well, and it's all making great sense. Alright, so that is it for Chapter 5. We'll pick back up next time with Chapter 6.